Hello there, and welcome to the Sleepy Space Channel. Tonight, we'll be drifting quietly toward the centers of galaxies, where gravity gathers into its slowest and most patient form. Far beyond the glow of stars, every galaxy carries a still point, hidden and steady. Supermassive black holes. Around them, light bends softly, and motion continues in long, quiet arcs that never seem to hurry. We begin close to home, in the calm heart of the Milky Way, before moving outward into deeper and older regions of space. If you enjoy these gentle journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here too. One sleepy soul at a time. But for now, there is nothing you need to do but settle in. Let your shoulders soften. Let your breathing slow. Allow your eyes to grow heavy. Let the day fade away. There is a kind of darkness that is not empty. It is the darkness between stars, between galaxies, between the slow turning arms of light that make up the structures we call home in this universe. It is not a void in any threatening sense. It is more like the darkness of a room at night, when you know the walls are still there, when you know the furniture has not moved, when everything familiar is simply resting in a quiet you cannot see but can feel. That kind of darkness is the one this journey begins in. Not the darkness of absence, but the darkness of presence, of things that are there, turning slowly, holding everything in place, waiting with the particular patience of objects that have been waiting for longer than stars have been burning. You might notice, as you settle in and let your breathing slow, that the universe is not a place of constant explosions and violent motion, though it certainly contains those things. The universe, taken as a whole, is mostly very slow. Stars take millions of years to form. Galaxies rotate once every few 100 million years. The largest structures in the cosmos drift apart at speeds that would take billions of years to produce any meaningful separation. When you look up at the night sky from somewhere dark enough to see it properly, you are not looking at a scene of chaos. You are looking at something orderly, patterned, and extraordinarily calm. The chaos is real, but it is folded inside structures that are, at their largest scales, remarkably quiet. We begin, as many journeys do, from somewhere familiar. The night sky above you, wherever you are listening from tonight, is a thin slice through the edge of the Milky Way. Our galaxy is a disk of stars, and we live inside it, somewhere out toward one of its spiral arms. When you look at the band of light that stretches across the sky on a clear night, you are looking along the plane of that disk, seeing the accumulated glow of hundreds of billions of stars stacked between you and the far edges of the galaxy. It is, when you think of it this way, less like looking at something distant and more like looking sideways through the room you are already inside. The Milky Way is not out there. It is here, all around you, and you are somewhere inside its slow turning. Galaxies, it turns out, all seem to share a common feature. They have centers. Not just geographic midpoints, but actual gravitational cores, places around which everything else moves, places that hold the rotation of the entire system in a kind of long, slow agreement. The arms of a spiral galaxy sweep outward from their centers and circle back, and then continue sweeping, in a motion that has been going on for so long that the idea of a beginning feels almost abstract. The center of a galaxy is not a decorative feature. It is structural. It is functional. It is, in the most literal sense, what holds the whole rotating thing together. And inside most of those centers, astronomers have found something extraordinary in its stillness. Not a star, not a cluster of stars, not a dense ball of glowing gas. Inside most large galactic centers sits an object of extraordinary mass compressed into a region of space that would, by stellar standards, be almost unremarkably small. These objects are supermassive black holes. They are the quiet anchors of the galaxies they inhabit. They are not, for the most part, doing anything dramatic. They are simply there turning slowly, holding the gravitational shape of everything around them, shaping the paths that light and matter follow across the breadth of an entire galaxy. There is something worth sitting with for a moment, as your breathing continues to slow and the sounds around you settle into the background. The idea that every galaxy we can observe appears to carry one of these objects at its center is not a small thing. It means that the structure of the observable universe, the trillions of galaxies spread across billions of light years, is organized around things we cannot see directly. The light of a galaxy comes from its stars. But the shape of that galaxy, the way it rotates, the pattern of its arms, the long history of whether it formed new stars or quieted into older light, all of that is influenced, in varying ways, by the invisible object at its center. The visible universe is, in a sense, organized around invisible things. Light itself is shaped by gravity. This is one of the quiet but fundamental ideas in modern physics. Light does not always travel in straight lines when space itself is curved. Instead, it follows the curvature of space-time, bending gently or dramatically depending on the mass it passes. Near a supermassive black hole, this bending becomes extreme. Light that would normally pass by continues instead into looping paths, or is redirected in ways that make the region around the black hole appear distorted when observed from far away. Even the photons that escape from nearby regions carry with them the imprint of this curvature, as if the geometry of space itself has left fingerprints on their trajectories. The feeling of this journey, from the very beginning, is one of drifting inward rather than looking outward. Most space exploration, in the imagination, involves moving away from the center, launching from a planet, escaping a gravity well, traveling towards something distant. But tonight, the motion is the opposite. We are drifting toward centers, toward the quiet things that anchor rotation, toward the objects that hold galaxies together without announcing themselves, without shining with their own light, without doing anything, most of the time, that would call attention to themselves. We are drifting toward the kind of presence that is felt rather than seen. The Milky Way is as good a place to begin as any. It is, after all, the galaxy we live inside. It is a wide, slowly rotating disk of somewhere between 200 billion and 400 billion stars, depending on how the outer edges are defined. It has a central bulge, a thickening of stars toward the middle, and from that bulge extend spiral arms that curve outward in long arcs, carrying younger stars, gas clouds, and dust along their slow orbital paths. The entire structure rotates, but not like a rigid object. Instead, different parts rotate at different speeds, a kind of differential motion that causes the spiral pattern itself to persist and evolve over time. From our position inside one of those spiral arms, the galaxy does not appear as a single structure in the sky. Instead, we see it edge on as a faint band of light stretching across the night. That band is the combined glow of countless stars layered along our line of sight. It is a reminder that we are not outside the galaxy, observing it as an object. We are inside it, part of its structure, moving along with it as it turns. The sense of stillness we experience from Earth is only apparent. In reality, we are moving through space at immense speeds, but those speeds are consistent and shared by everything around us, which is why they feel like rest rather than motion. And at the center of all that turning is something we cannot see with our eyes. The core of the Milky Way is hidden behind dense clouds of gas and dust that block visible light almost completely. What lies beyond that veil is not invisible in all wavelengths, however. Infrared light, radio waves, and other forms of radiation pass through more easily, allowing astronomers to peer into the region indirectly. What they observe is a crowded environment of stars moving in tight, fast orbits around an unseen central point. These motions are not random. They are structured, precise, and consistent with the presence of an extremely massive object occupying a very small region of space. From these observations, the conclusion becomes clear. At the center of the Milky Way sits a supermassive black hole. It does not glow. It does not emit light in any conventional sense. It does not announce its presence through brightness or color. Instead, it reveals itself through the motion of everything around it. Stars close to the center move at high speeds, tracing elliptical paths that curve tightly around an invisible focal point. The closer they are, the faster they move, as if orbiting something immensely concentrated. This central object has a mass of roughly 4 million times that of the Sun, yet it is contained within a region of space smaller than the orbit of Mercury. That combination of mass and compactness leaves no ordinary astrophysical explanation. It is not a cluster of stars, because such a cluster would produce light and would not remain stable over long periods. It is not a dense cloud of gas, because such a cloud would collapse and ignite into star formation. It is, instead, something more extreme in its gravitational behavior, a region where matter has been compressed beyond the point at which conventional structures remain possible. What makes this especially striking is not just the object itself, but the fact that it has been shaping the galaxy for billions of years without ever needing to be seen directly. The orbits of stars across the Milky Way, the structure of the galactic disk, the long-term stability of the spiral arms, all of these are influenced, in subtle ways, by the gravitational presence at the center. The galaxy is not built around something visible. It is built around something inferred, something known only through its effects. And yet, this is not unique to our galaxy. Across the observable universe, nearly every large galaxy appears to contain a similar central object. Some are smaller, some larger, some relatively quiet like the one in the Milky Way, and others far more active in earlier phases of their history. But the pattern repeats. Wherever there is a sufficiently large galaxy, there is almost always a central supermassive black hole anchoring its structure. This repetition across vast distances and times suggests something fundamental about how galaxies form and evolve. The presence of a central black hole is not an accident. It is part of the architecture of galaxy formation itself, emerging naturally as gas collapses, stars form, and gravitational structures deepen over time. The black hole grows alongside the galaxy, shaped by the same inflows of matter that build the galactic bulge and disk. In turn, its presence influences how that matter behaves, regulating how much gas turns into stars and how much remains available for further growth. Over billions of years, this relationship settles into a kind of balance. The galaxy becomes a large, structured system of stars, gas, and dark matter, while the central black hole becomes a compact, massive anchor that no longer grows rapidly except under special conditions. Most of the time, it is quiet. It does not consume large amounts of matter. It does not shine brightly. It simply exists, holding the center of the galaxy in a stable gravitational configuration. This quiet state is not unusual. In fact, it is the most common state for supermassive black holes across cosmic time. The dramatic, highly luminous phases when black holes are actively feeding and producing enormous radiation from surrounding accretion disks are relatively brief compared to the long periods of inactivity that follow. In those quieter periods, the black hole remains present but subdued, its influence continuing primarily through gravity rather than energetic emission. Seen in this way, The center of a galaxy is not a place of constant activity, but a region of long-term stability. It is a point around which everything else moves, slowly and predictably, over timescales that far exceed human experience. The stars orbiting it will complete many revolutions before any significant change occurs in the structure of the galaxy itself. Even the galaxy's future evolution merges with other galaxies, changes in star formation, gradual shifts in shape, unfolds on timescales so long that each phase blends almost seamlessly into the next. And through all of this, the central black hole remains. It is not a dramatic presence in the everyday sense. It does not dominate the sky with brightness or motion. Instead, it defines a kind of gravitational stillness at the heart of motion itself. Everything in the galaxy moves around it, and yet it does not need to move in order to shape that motion. Its presence is enough. As you continue to settle into this quiet moment, there is something gently stabilizing about that idea. The universe is not random motion without structure. It is not chaos unfolding without pattern. It is a system of immense scales, slow rhythms, and long-term balance, where even the most extreme objects, black holes with masses measured in millions or billions of suns, behave according to consistent principles of gravity and space-time. And at the center of it all, whether seen or unseen, whether active or quiet, the same pattern repeats. A presence that does not need to announce itself in order to be real. A structure that holds everything else in motion without itself needing to rush. The Milky Way moves the way a slow river moves, not rushing, not still, but drifting, in a direction that has been set by forces too large to feel from inside them. The stars of the outer arms complete one full orbit of the galactic center over a span of time longer than the current age of the Earth. Out toward the edge, where the density of stars begins to thin and the dark matter halo becomes the primary gravitational influence, the orbital periods stretch even longer. Everything is turning. Everything is following a path shaped by the mass at the center. And the center, as you might now begin to expect, is not just a dense cluster of stars, though there are many of those near the middle. The center is something else. The innermost region of the Milky Way is a place of considerable density. Stars there are packed far more tightly than in the neighborhood of the solar system. Where our sun sits relatively isolated in its part of the galaxy, the nearest star, several light-years away, near the galactic center, stars can be separated by distances that would place a neighbor within our own solar system by comparison. The inner galaxy is crowded by stellar standards. But even in that crowded region, the thing that organizes everything else is not any of the stars. It is the object at the very center, around which even those densely packed stars are orbiting. That object has been given a name taken from the region of the sky where it appears to reside. Sagittarius A star, written with an asterisk to indicate that this is the compact central source, rather than the broader complex of gas and stars in the same direction. It is a supermassive black hole. Its mass is somewhere in the range of 4 million times the mass of the Sun. Not 4 million suns in volume, the way a large star might be. Not 4 million suns in physical extent. 4 million solar masses compressed into a region of space that, in the context of a galaxy, is almost impossibly small. The boundary of the region from which nothing can return the event horizon would fit within the orbit of Mercury around our own Sun. The entire object, in terms of the space it occupies, is smaller than the distance from the Sun to its innermost planet. And yet it outweighs 4 million stars, like ours. There is something about this compression that the mind wants to resist. We are used to thinking of large masses as occupying large spaces. A heavier thing is usually a bigger thing in the experience of everyday objects. But at the extreme end of density, at the end of stellar evolution, when a massive enough core collapses, the relationship between mass and space changes completely. The mass is real. It has gravitational effects that extend across many light years in every direction. The space it occupies, however, is almost incomprehensibly small. Sagittarius A star weighs 4 million times as much as the Sun and fits inside the orbit of Mercury. The event horizon of a black hole is not a surface in the way that a planet's surface is. It is not a physical boundary that something would bump into. It is a geometric feature of spacetime, a location in space beyond which the curvature of spacetime becomes so extreme that no path leading outward exists anymore. Cross that boundary, and every possible direction of travel leads further inward. There is no trajectory that can return you to the region outside. The event horizon is not a wall. It is a point of no return built into the geometry of space itself. It is, in a strange way, more like a rule than a surface. For a black hole of 4 million solar masses, that boundary exists at a particular distance from the center. And one of the curious things about black holes is that the larger they become, the more gently curved spacetime is at their event horizon. A small black hole, the kind formed by the collapse of a single star, has a tiny event horizon, and the curvature of spacetime there is extreme. The tidal forces near the event horizon of a small black hole would pull any approaching object apart long before it reached the boundary. But for a supermassive black hole of 4 million solar masses, the event horizon is large enough that the tidal forces at the boundary itself are, comparatively, much gentler. An object approaching the event horizon of Sagittarius A star would not necessarily feel anything unusual at the moment of crossing. The geometry would have already claimed it, but the physical sensation at that moment would be far less dramatic than intuition suggests. This is one of the reasons that supermassive black holes have a quality of quiet about them that smaller black holes lack. The mathematics of curvature and tidal force means that the larger the event horizon, the more gradual the transition from ordinary space to the space beyond the point of no return. The extremity is real, but it is spread across a larger region. The approach is, at the scale of the event horizon itself, almost gentle. The violence, to whatever extent it exists, is concentrated much closer to the center, inside the boundary, where we cannot observe it in any case. The stars nearest to the center of the Milky Way have been watched for decades now, tracked over their orbits with instruments sensitive enough to detect their motion. Some of these stars complete full orbits of the galactic center in just a few years, which sounds like a long time. But for an orbit measured in light hours of radius around an object 4 million times the mass of the Sun, this orbital period is actually quite short. The orbital periods of these stars, combined with the measured size of their orbits, allow astronomers to calculate the mass of the central object through the same equations that govern the orbit of any object around any gravitational source. The mass they calculate is consistent across different stars, different orbits, different observational methods. There is something there, at the center, with a mass of 4 million suns contained within a very small region. The orbits are the clock by which that mass is read. Watching those stars move, some of them traveling at fractions of a percent of the speed of light as they swing around their closest approach to the center, there is a particular feeling that the mathematics carries. These are not small objects. These are stars. Real stars, with masses comparable to or greater than our own Sun, traveling at speeds that feel extreme in human terms, sweeping around the galactic center in tight, looping orbits. And yet what is pulling them is invisible. The center of those orbits emits no light at the wavelengths we most easily see. It is inferred entirely from the motion around it, the way you might infer the presence of something you cannot see by watching how the things around it move. There are moments when Sagittarius A star is not entirely quiet. Hot clouds of gas occasionally pass near the central region, and as they approach the gravitational influence of the black hole, they can heat up and emit radiation briefly before they disperse or are consumed. These events produce flares, brief brightening in the radio and infrared light from the galactic center that rise and fade over minutes to hours. They are not dramatic in any cosmic sense. They are more like small disturbances passing through an otherwise calm region, brief interactions between infalling material and the extreme gravitational environment near the center. The flares come and go. The central object remains. What is most striking about Sagittarius A star, when you consider it as a whole, is how quiet it is in its current state. 4 million solar masses, sitting at the center of a galaxy of hundreds of billions of stars, and for the most part, it is simply there. It is not consuming large quantities of material at the moment. It is not producing the kind of dramatic outflows seen in the most active galactic centers. The dust clouds and stellar winds of the inner galaxy provide a slow trickle of material, and occasionally a gas cloud provides a small meal. But by the standards of what supermassive black holes are capable of, our own galactic center is in a remarkably quiet phase and has been for a long time. Sagittarius A star is a gravitational anchor in its most settled, most patient state. That settled quality is worth dwelling on. There is something in the idea of 4 million solar masses sitting quietly at the center of a slowly turning galaxy, maintaining the shape of that rotation through nothing more than the patient fact of its gravitational presence that carries a particular kind of calm. It is not doing anything. It is not producing energy in dramatic quantities. It is not shining. It is simply there, and its being there is enough to organize the motion of hundreds of billions of stars across a disk, 100,000 light-years across. Presence, in the cosmos, does not require activity. It does not require brightness or drama or announcement. The heaviest things can sit the most quietly. They do not need to call attention to themselves. Everything around them already knows they are there, in the way that everything already knows where the center of gravity is, not through awareness, but through the simple fact of moving in the paths the geometry provides. The long-term stability of Sagittarius A star is another aspect of its quietness. The Milky Way is several billion years old, and the black hole at its center has been there, in some form, for most of that time growing slowly, accumulating mass across enormous stretches of cosmic history, but always present, always shaping the galactic rotation. Over those billions of years, the galaxy has gone through periods of more active star formation and periods of quiet. It has accreted gas, experienced mergers with smaller galaxies, absorbed dwarf galaxies into its outer regions. Through all of that, the center has persisted. The black hole has grown slowly, but it has always been there. It is one of the most stable structures in the galaxy, perhaps the most stable, by virtue of its enormous mass and its deep gravitational anchor at the center of everything. When you lie in the dark tonight and think of the Milky Way, you can think of it as a wide, slowly turning disk of light, which it is. And at the center of that disk, invisible behind dust and distance, something with the mass of 4 million suns sits quietly, holding the whole rotation in place. The stars sweep around it. The spiral arms extend outward from it. The galaxy moves around it. And it simply waits, in the way that only very massive things can wait, with a patience that has no relationship to impatience, because it has never known the alternative. The center is near and unreachable at the same time. It is part of the galaxy we live inside, closer in some directions than the far edges of the Milky Way's outer arms. and yet it is hidden behind dust that visible light cannot penetrate, separated from us by 26,000 light-years, surrounded by one of the densest stellar environments in the galaxy. We know it is there. We can read its mass in the orbits of stars that have been tracked for decades. We can see the brief flares of light when gas passes near it. We have even seen, in composite images assembled from radio telescope data gathered across the whole Earth, the shadow it casts against the glow of surrounding material, a dark circle surrounded by a ring of light bent by the extreme gravity of the event horizon. We know it is there. We know it is massive. We know it is quiet. And we cannot go there, and we cannot see it directly. And that combination of certainty and distance gives it a quality that few things in human experience can match. The galaxy turns around its center, and the center holds. The stars orbit without complaint, following the geometry of space-time that 4 million solar masses has shaped over billions of years. And somewhere out in one of the spiral arms, a small star and its family of planets complete their own long orbit of that center once every 225 million years or so. The last time the solar system was in the same position in the galaxy it occupies tonight, the first dinosaurs had not yet appeared on Earth. The time before that, the first fish was still new. The galaxy turns slowly, and the center holds, and everything moves in the patient agreement that gravity produces between mass and the things that surround it. There is a sense, in all of this, that the center is not remote. It is not something separate from the galaxy that we observe from outside. It is the thing around which we are already turning, already orbiting, already caught in the long, slow gravitational agreement that makes the Milky Way the particular shape it is. We are not looking at the center from outside. We are inside it. We are part of the turning. And the quiet thing at the middle of that turning is as much a part of our cosmic home as the stars we can see on any clear night. The pattern repeats. This is one of the things the universe does with particular consistency. It repeats its structures across different scales and different locations, so that what you find in one place turns out to be, in its essential form, present in another. The Milky Way has a supermassive black hole at its center. So does every large galaxy that astronomers have been able to examine in sufficient detail. The pattern is not occasional. It is not a curiosity that appears in some galaxies and not others. It appears to be universal, or close enough to universal that any exception would demand explanation. Every large galaxy carries a supermassive black hole at its center, the way every large galaxy carries a central gravitational bulge. The two are not coincidental, they are related, and they have been growing together since early in the history of the universe. The galaxies nearest to the Milky Way are the ones we can observe in the most detail. The local group, as astronomers call the small cluster of galaxies of which the Milky Way is a member, contains a few dozen galaxies of various sizes. Most of them are small dwarf galaxies that contain hundreds of millions of stars rather than hundreds of billions. But the largest members of the local group are proper spiral or elliptical galaxies, and the largest of all the Andromeda Galaxy is a spiral galaxy comparable in size to the Milky Way, and it too has a supermassive black hole at its center. The mass of Andromeda's central black hole is considerably larger than that of Sagittarius A star. It is not 4 million solar masses, but something in the range of tens of millions, perhaps more. The galaxy is larger, the black hole is larger, and the two have grown together across the same cosmic timescales. When you look at a galaxy from outside, from the perspective of an observer at sufficient distance, the black hole at the center is not something you can see directly. What you see is the galaxy itself, the glow of its stars, the shape of its arms, if it is a spiral, the smooth elliptical shape, if it is an older galaxy that has used up its star-forming gas. The black hole is hidden within the central regions, detectable only through the motion of stars and gas near the center, or through the occasional signs of activity when it is consuming material. Most of the time, most galactic centers look exactly like what they are: very dense collections of old stars arranged around a gravitational center that emits no light of its own. The idea of galaxies as carriers of their central black holes, the way living things carry their genetic information, not visibly, but structurally, shaping what they do and how they develop, is a useful one, if not taken too literally. A galaxy and its central black hole are not separate things that happen to be in the same place. They are parts of the same system, grown together, shaped by each other's gravity, both influenced by the same infalling gas, and the same mergers, and the same long history of accumulation. When a galaxy forms, the black hole at the center forms with it, or shortly after. When a galaxy merges with another galaxy, the black holes from both galaxies eventually find each other and merge as well. The center of a galaxy is not an add-on. It is fundamental to what the galaxy is. Among the nearby galaxies, there is variation in how active the central black holes are at any given time. Most are quiet, in a low-feeding state, where they are not consuming significant quantities of material and are therefore not producing significant quantities of radiation from the immediate surroundings of the event horizon. But some of the nearby galaxies show mild activity signs that their central black holes are consuming a small but meaningful amount of material, producing a low-level glow from the inner region that is detectable with the right instruments. These mildly active centers are interesting precisely because they show what a supermassive black hole looks like in a transitional state, not fully quiet, not dramatically active, but somewhere in between. The activity level of a galactic center is primarily determined by how much material is reaching the vicinity of the black hole. When gas clouds fall inward, when stellar winds from the dense central star cluster carry material toward the center, when some gravitational disturbance in the inner galaxy sends a stream of gas inward, these events provide fuel. The black hole does not seek out material. It simply sits at the center of its gravitational well, and material that happens to lose enough momentum falls inward, heats up as it spirals through the surrounding region, and eventually either crosses the event horizon or gets redirected outward by the complex magnetic and radiation environment near the center. Whether any of this is happening, and how much of it, determines whether the galactic center appears quiet or active in our observations. The orbits of stars around galactic centers in other galaxies are harder to observe than those around Sagittarius A star, simply because other galaxies are much farther away. Even the nearest galaxies are hundreds of thousands of light-years distant, which means the individual stars near their centers are not distinguishable as separate points of light with most instruments. But the overall motion of gas and stars in the inner regions of other galaxies can be measured using the Doppler effect, the way the light from something moving toward an observer is shifted to slightly shorter wavelengths, and the light from something moving away is shifted to longer ones. When the inner region of a galaxy shows gas rotating very rapidly around a small central area, that rapid rotation reveals the mass of whatever is at the center. The same equations that work for individual stellar orbits around Sagittarius A star work for the statistical motion of many stars and gas clouds around the centers of more distant galaxies. The physics does not care about the distance between the observer and the system being observed. What these observations reveal, across hundreds of galaxies that have been studied in this way, is the same pattern repeated at different scales. Every large galaxy has a central mass concentration that is far too dense to be explained by any normal collection of stars. Every one of those mass concentrations has properties consistent with a supermassive black hole. The right mass, the right compactness, the right gravitational influence on surrounding material. The repetition is so consistent that astronomers now treat the presence of a supermassive black hole at the center of a large galaxy not as something that needs to be proven in each individual case, but as the default expectation, to be refined by measurement in each specific instance. There is something calming about that kind of universality. The universe, it turns out, does not produce galactic centers in a random or arbitrary way. It produces them according to physical principles that operate the same way in every location at every scale at which they apply. The Milky Way's center is not a quirky exception to some other rule. It is an instance of the standard pattern. Andromeda's center is an instance of the same pattern. Every galaxy you might observe from the most sensitive telescope ever built is, in all likelihood, another instance of the same pattern. The universe has a way of organizing matter around invisible, dense centers of gravity, and it applies this organizational principle on the scale of galaxies with the same reliability that it applies the orbital mechanics of planets on the scale of solar systems. Gravity is the organizing force of the cosmos, and supermassive black holes are its most extreme expression at the scale of galaxies. They are not accidents. They are not anomalies. They are, in a very real sense, expected, even necessary features of the structures that gravity builds when given enough matter and enough time. The quiet, massive objects at the centers of galaxies are not strange exceptions to how the universe normally works. They are how the universe normally works at this particular scale, over these particular timescales. They are the rule, not the exception. And the rule, it turns out, is very quiet indeed. The repetition of this pattern across the observable universe, from the nearest galaxies in the local group to galaxies so distant that the light reaching us left them when the universe was young, gives the cosmos a kind of structural coherence that the imagination can rest in. Things behave the same way in distant places as they do in nearby ones. The physics that governs the orbit of a star around Sagittarius A star is the same physics that governs the orbit of a star around the black hole at the center of a galaxy a billion light-years away. There is no point in the observable universe where the rules change. Gravity works the same way everywhere. Mass produces curvature in space-time everywhere. Orbits follow the same mathematical relationships everywhere. The universe is not arbitrary. It is, in the deepest sense, consistent. And in that consistency, at this particular moment of quiet lying in the dark, there is something that feels almost like reassurance. Most supermassive black holes spend most of their time in silence. They sit at the centers of galaxies, massive and patient, shaping the orbital paths of nearby stars without doing anything that would call attention to themselves from a distance. They are invisible to any telescope pointed at them in ordinary light. They are detectable only through inference, through the motion of things nearby, through the gravitational bending of light from more distant sources, through the faint signals that very sensitive instruments can detect from hot gas in the immediate surroundings. Most of the time, most galactic centers are just dark, heavy and dark, and patient in their silence. But that is not always the case. And it has not always been the case throughout the history of the universe. There are conditions under which a supermassive black hole becomes dramatically visible, conditions under which it outshines every star in the galaxy it inhabits, producing more light from a region the size of the solar system than an entire galaxy of hundreds of billions of stars. These conditions are rare, and they are temporary. But they are real, and the objects produced by them were among the most luminous things ever to exist in the history of the observable universe. The first thing to understand about this brightness is that it does not come from the black hole itself. A black hole is, by definition, an object from which light cannot escape. The event horizon is a boundary across which no information travels outward. The black hole is dark. What produces the light is the material falling toward the black hole, the gas and dust that, as it spirals inward under gravity, heats up to temperatures far beyond anything in ordinary stellar experience. That heated, infalling material glows. It glows intensely. It produces radiation across a wide range of wavelengths, not just visible light, but also ultraviolet radiation, X-rays, and other energetic forms of electromagnetic energy. The black hole itself remains dark. But the region around it, when sufficient material is falling inward, becomes extraordinarily bright. The structure that forms around an actively feeding supermassive black hole is called an accretion disk. As gas spirals inward, conservation of angular momentum prevents it from falling straight in it, instead forms a rotating disk, gradually losing energy and angular momentum through friction and magnetic processes, slowly spiraling inward toward the event horizon. The inner regions of this disk, where the material is moving fastest and the gravitational forces are most extreme, reach temperatures of millions of degrees. At those temperatures, the material does not glow red or orange or even white hot. It glows in X-rays and ultraviolet light. It is among the hottest material in the universe, produced not by nuclear fusion, but by the gravitational compression of infalling gas as it circles toward the point of no return. Around the outer regions of the accretion disk, more complex structures can form. Strong magnetic fields, twisted and accelerated by the rotating material, can funnel some fraction of the infalling energy outward, not inward, producing powerful jets of material that stream away from the vicinity of the black hole along the poles of the system, at right angles to the plane of the accretion disk. These jets can extend for distances that dwarf anything else in the observable universe. Some of them reach lengths measured in millions of light-years, extending from their host galaxy far out into the surrounding intergalactic space. They are among the largest single coherent structures in the cosmos, formed by processes concentrated in a region not much larger than the solar system. The jets are not streams of matter in the way that a river is a stream of water. They are structured outflows of plasma-ionized gas threaded through with magnetic fields, moving at velocities approaching the speed of light in their innermost portions. Where they meet the intergalactic medium, the thin gas that fills the space between galaxies, they produce large lobes of radio-emitting material that can be detected from very great distances. Radio telescopes on Earth can observe these lobes even when the galaxy producing them is billions of light-years away. The jets are vast, and they are visible, and they are one of the clearest signatures that a supermassive black hole is actively consuming material in large quantities. The class of objects produced when a supermassive black hole is feeding at high rates, when a large accretion disk is fully formed and active, producing tremendous luminosity from a compact central region. These are what astronomers call quasi-stellar objects, or quasars. The name comes from their original discovery when they appeared in early radio surveys as compact sources of radio emission that were then associated with objects that looked, in optical telescopes, like faint stars, but were found to be at enormous distances. At those distances, anything as luminous as a star would be completely invisible. So these point-like objects, glowing at stellar brightness from billions of light-years away, had to be producing energy at a rate that vastly exceeded any star. What were they? The answer, worked out over many years of observation and theorizing, is that they are the active feeding phases of supermassive black holes. When the conditions are right, when a sufficiently massive black hole has access to a sufficiently large supply of infalling gas, the system produces luminosity that exceeds the combined light output of the entire host galaxy, by factors of hundreds or thousands. A quasar can outshine its entire galaxy so completely that the galaxy itself is invisible in the background glow of the central source. From billions of light years away, you see the quasar, the pinpoint glow of the active center, and the galaxy around it is lost in the brightness. They are the most luminous, sustained phenomena in the universe, and they are produced by matter falling into a gravitational well. But here is where the quiet returns. Quasars are not permanent. They are phases. A supermassive black hole in a quasar phase is feeding on material at a high rate, but that material is not unlimited. As the available gas in the surrounding region is consumed or expelled by the energy output of the accretion disk, the supply eventually decreases. The accretion rate falls. The luminosity drops. The jets quiet down. The accretion disk cools and disperses. And the supermassive black hole, now somewhat more massive than it was before its active phase, settles back into the quiet state that is its most common mode. The quasar phase ends, and the galaxy around it continues its quiet evolution, its central black hole, now heavy and dark and patient once again. This means that most of the quasars we observe are not the present-day state of those galactic centers. They are the past. Because light takes time to travel across the universe, when we observe a quasar at a distance of 10 billion light-years, we are seeing light that left that system 10 billion years ago. We are seeing the universe when it was young, when galaxies were still building up, their gas supplies and central black holes were in their most active feeding phases. The universe was brighter then, at its core richer in quasars, richer in active galactic centers, richer in the kind of extreme luminosity produced by rapid feeding. Over time, as the gas was consumed and the available fuel for quasar activity decreased, the population of active galactic centers has declined. The universe has quieted. That quieting is itself a kind of cosmic history, the history of how the universe's most dramatic phase settled into the more sedate structures we see around us today. The Milky Way is a quiet galaxy in a relatively quiet phase of cosmic history. Its central black hole is not currently feeding at anything approaching quasar rates. The local universe, compared to the universe of 10 billion years ago, is a much quieter place. The bright phase has passed for most of the galaxies we can see nearby. What remains are the settled, massive, quiet things, the supermassive black holes at the centers of mature galaxies, carrying the weight of their former feeding phases, holding their galaxies in place, no longer burning with the intensity that once made their ancient counterparts visible from across the observable universe. There is something in this arc, from brightness to quiet, that feels familiar in a soft way. The most dramatic phases of things are not permanent. They are intense, and then they settle. The universe burned bright in its youth, with quasars lighting up galactic centers across billions of light-years. And now, billions of years later, those same centers are quiet. The black holes that once outshone entire galaxies are now invisible. They are heavy with the mass they accumulated during that active phase, sitting patiently at the centers of their galaxies, holding everything in place without making any noise. The brightness was real and important, and part of how the universe built the structures it now contains. But the brightness was also temporary. And what remains after the brightness passes is the quiet, the heavy, patient, invisible quiet of a mature, supermassive black hole doing nothing more dramatic than being there. The light from ancient quasars is still reaching us. When you look at the deep universe through the most sensitive telescope, You are seeing ancient light from ancient active centers galaxies in their youth, feeding intensely, shining across distances so vast that the universe has changed dramatically by the time that light arrives. The quasars that produced that light are almost certainly quiet now. The galaxies that surrounded them have aged, used up their gas, slowed their star formation. The bright things have become dark things. The ancient light is the only record of what those centers were like when they were young. And it is drifting through the universe still, arriving here, falling gently on the mirrors of our telescopes, carrying information about a time when the universe was not yet quiet. Even the idea of brightness at these distances becomes soft. A quasar, 10 billion light-years away, is not something you can see with the naked eye on a dark night. It is a point of light detectable only with sensitive instruments, distinguishable from nearby stars only by the careful analysis of its spectrum. The brightness exists in an abstract sense. The luminosity is real, enormous, one of the most energetic processes in the observable universe. But at the distances involved, it arrives at us gently, as a faint signal in a sensitive detector. The universe has enough space to soften even its most extreme brightness into something that falls quietly. Across the most massive galaxies in the universe, there are central objects that stretch the meaning of large into something almost purely conceptual. These are not simply supermassive black holes in the everyday astronomical sense of millions of solar masses. They sit far beyond that familiar range, occupying the upper reaches of what gravity can assemble over cosmic time. Their masses rise into the billions of solar masses, placing them in a category sometimes described as ultramassive, though even that word feels like a gentle attempt to label something that is already beyond ordinary intuition. At this scale, the idea of comparison begins to lose its usual sharpness. A black hole of 1 billion solar masses is not just a scaled-up version of something smaller in the way a larger star is still recognizably a star. The difference between a few million and a billion solar masses is not a small extension along a familiar line. It is a shift into a regime where geometry, distance, and time itself begin to take on new proportions. The event horizon expands accordingly, forming a boundary so wide that it would encompass entire planetary systems without any need for compression or distortion. What once seemed vast becomes contained. Yet even here, in this extreme range, the physics remains remarkably calm in its behavior at the edge. The event horizon of such a massive object does not behave like a violent surface. It is not a place of impact or collision in the ordinary sense. Instead, it is a boundary defined entirely by the structure of space-time, where the distinction between outward escape and inward fall is determined by geometry alone. At these enormous scales, the curvature at the horizon becomes relatively gentle in local terms. An object passing across it would not necessarily experience any sudden physical disruption at that exact moment. The change is global, not local, unfolding in how paths through space-time are defined, rather than in any sharp physical threshold. These ultramassive black holes tend to reside in galaxies that are themselves among the most evolved structures in the cosmos. Giant elliptical galaxies, often formed through repeated mergers over billions of years, provide the calm, aged environments where such extreme central masses can exist. These galaxies are not typically active in the way younger spiral galaxies are. They contain fewer cold gas reservoirs, lower rates of star formation, and a general sense of long-term settling. Their stellar populations are older, redder, and more evenly distributed, giving the entire system a quieter appearance when viewed on cosmic scales. At the heart of these galaxies, the central black holes reflect the same long history of accumulation and regulation. Their enormous masses are not the result of a single event or a short-lived phase of rapid growth. Instead, They are the outcome of extended cycles of feeding, feedback, and gradual adjustment between black hole and galaxy. During periods of active accretion, gas falls inward toward the central region, forming a hot, luminous disk that radiates enormous amounts of energy. That energy, in turn, interacts with the surrounding gas, heating it and often pushing it outward, reducing the very material that fuels further growth. This self-regulating process creates a long-term balance between the black hole and its host galaxy. As the black hole grows, its ability to influence its surroundings increases, and this influence eventually limits further rapid growth. The result is not an unbounded accumulation, but a kind of equilibrium shaped by feedback. Over time, this produces a relationship between the mass of the central black hole and the mass of the galaxy's central bulge. Across many galaxies, this relationship remains surprisingly consistent, suggesting that the growth of both structures is deeply linked rather than independent. In this way, ultramassive black holes are not anomalies, but records of scale. Their mass reflects the size and history of the galaxy that formed them. A larger galaxy, with more material available during its active phases, has the potential to build a larger central black hole. But that growth is never unchecked. The same energy output that allows the black hole to grow also eventually limits its ability to continue growing at the same pace. The system gradually settles into a long, stable configuration where neither component dominates the other in an explosive way. What is striking about these extreme objects is that nothing in their underlying physics changes simply because they are larger. The same equations that describe the motion of planets around stars also describe the motion of stars around galactic centers and the behavior of gas near event horizons. General relativity does not introduce new rules at higher masses. Instead, it continues to apply the same structure of space-time geometry consistently across all scales. The difference is not in the laws themselves, but in how those laws manifest when the numbers become enormous. This continuity gives the universe a kind of structural coherence. A black hole of stellar mass and a black hole of billions of solar masses are governed by the same fundamental principles. Accretion disks form in both cases through the same general mechanism of inward spiraling matter, losing angular momentum and heating as it approaches the central region. Jets, when they appear, arise from similar interactions between magnetic fields and rotating plasma near the event horizon. The details change with scale, but the underlying patterns remain consistent. As mass increases, certain effects become more gradual rather than more extreme. The curvature of spacetime near the event horizon becomes less sharply curved over small distances, meaning that tidal forces at the horizon can actually be weaker for very large black holes than for smaller ones. This leads to the counterintuitive result that crossing the event horizon of an ultramassive black hole could, in principle, feel less physically dramatic than crossing the horizon of a smaller one, even though the overall structure is vastly larger. The galaxies that host these objects are often the endpoints of long evolutionary histories. Many have formed through multiple mergers with other galaxies, gradually accumulating mass and settling into large spheroidal structures. Over time, their internal gas reservoirs become depleted, reducing the rate of new star formation. Without large supplies of cold gas, the galaxy's ability to form new luminous stars diminishes, and its overall brightness slowly shifts toward longer, redder wavelengths dominated by older stars. In this quieter environment, the central black hole persists as one of the most stable components. It does not require ongoing activity to remain present. Even in periods when little material is falling into it, it continues to exist as a massive gravitational feature at the center of the galaxy. Its influence is primarily structural rather than active, shaping the orbits of nearby stars and maintaining the overall gravitational symmetry of the galactic core. The existence of ultramassive black holes also reflects the long timescales over which galaxies evolve. These are not structures formed quickly or in isolation. They are the result of billions of years of gradual change, interaction, and accumulation. Each merger, each phase of accretion, each period of feedback contributes to the final mass of the central object. In this sense, the black hole becomes a kind of integrated history of the galaxy itself, encoding in its mass the cumulative effects of processes that unfolded over cosmic time. Despite their scale, these objects remain fundamentally consistent with the rest of the universe. There is no threshold at which they stop behaving according to known physical laws. Instead, they extend those laws into regimes of mass and size that challenge human intuition but not mathematical description. The same gravitational principles that govern smaller systems continue to apply, simply operating on larger numbers and longer timescales. This consistency is one of the quiet features of the universe. It does not change its rules as things become larger or older. Instead, it allows the same structures to repeat at different scales, producing galaxies, stars, and black holes that differ in size but not in underlying behavior. Ultramassive black holes are part of this continuity. They are not exceptions, but extensions of the same gravitational logic that governs everything from planetary motion to the large-scale structure of the cosmos. In the end, what defines these objects is not activity, but endurance. They do not need to be active to remain significant. They do not need to shine or emit energy to shape their environments. Their presence alone is enough to influence the structure of entire galaxies. Sitting at the centers of massive elliptical systems, they represent one of the most stable forms of structure the universe can produce. Regions of extreme mass, quietly embedded in space, persisting through eras of change that reshape everything around them. And in that persistence, there is a kind of stillness. Not emptiness, not absence, but a steady continuation of gravitational presence that remains unchanged while everything else in the galaxy slowly evolves around it. The mass that makes a supermassive black hole what it is did not arrive all at once. Nothing at cosmic scales arrives all at once, or if it does, the cosmic scale absorbs the event into a longer story that makes the sudden arrival seem, in retrospect, part of a gradual process. The growth of a supermassive black hole is fundamentally a story of accumulation, slow, patient, incremental addition of mass across timescales that dwarf any human frame of reference. 1 billion years is not a long time in this story. 10 billion years is more like it. And across that span of time, the steady spiraling inward of gas, the occasional merger with another black hole, the slow settling of matter through the gravitational funnel of the galactic center, all of these processes add, grain by grain, in cosmic terms, to the total mass of the central object. The primary mechanism of growth for most of cosmic history has been accretion, the spiraling inward of gas through an accretion disk. Gas does not fall straight into a black hole. It enters the gravitational influence of the central object with some angular momentum, some sideways motion, and that angular momentum has to go somewhere before the gas can spiral all the way to the event horizon. The process by which angular momentum is transferred outward, allowing material to spiral inward, involves friction, turbulence, and the twisting of magnetic fields through the rotating gas. This is not a fast process. Material in the outer regions of an accretion disk may take thousands of years to work its way inward to the event horizon. The process is measured, gradual, unhurried. The rate at which a black hole can consume infalling material is also physically limited. As the infalling gas heats up and radiates energy, some of that energy pushes back against the inflow, opposing the gravity that is pulling the gas inward. At high enough accretion rates, this outward radiation pressure can slow or even halt the inflow entirely. There is a natural limit to how fast a black hole of a given mass can consume material, a rate at which the outward radiation pressure exactly balances the inward gravitational pull. This limiting rate is proportional to the black hole's mass. A more massive black hole can consume material at a higher absolute rate before reaching this limit. This means that as a black hole grows, its capacity to grow further also increases, which explains in part how the largest black holes became so large over cosmic history early. Rapid growth expanded their capacity for further growth. But even with this increasing capacity, the process remains slow by any human standard. A supermassive black hole, growing at its maximum theoretical rate, would double its mass on a timescale of tens of millions of years. Most black holes spend most of their time consuming material at rates well below the maximum, sometimes far below. The active quasar phases, when feeding rates are high, are relatively brief episodes in the long life of a galactic center. Most of the time, as we have noted, the feeding is slow or nearly absent. So the accumulation of mass is mostly a very slow drip, punctuated by occasional episodes of more intensive consumption spread across billions of years. The second major mechanism of growth is the merging of two black holes when their host galaxies merge. Galaxies are not static objects fixed in isolation. They are parts of groups and clusters, and they interact with each other gravitationally. When two galaxies of comparable size approach each other, their mutual gravity draws them together in a long, spiraling encounter that eventually results in a merger, the two distinct galaxies combining into a single, larger galaxy. This process, which happens frequently over cosmic history, has major consequences for the central black holes of the merging galaxies. When two galaxies merge, their central black holes do not immediately find each other and merge as well. The galaxies themselves merge first, the stars and gas of the two systems intermingling and eventually settling into the gravitational potential of the combined system. The central black holes, carried along by the bulk motion of the galaxies they inhabit, eventually find themselves orbiting each other in the merged galaxy's central region. They form a binary system, two massive black holes circling each other at the centers of the merged galaxy, each pulling on the other with enormous gravitational force. This binary system takes a very long time to resolve. As the two black holes orbit each other, they interact with the stars and gas in the surrounding region, gradually losing energy and angular momentum and slowly spiraling closer together. Over millions or billions of years, the separation between the two black holes decreases. The orbital period shortens. The orbital velocity increases. And eventually, when the two objects are sufficiently close, another mechanism takes over: the emission of gravitational waves. Gravitational waves are ripples in the fabric of space-time, produced by accelerating masses. Any two massive objects orbiting each other produce gravitational waves. The Earth-Moon system produces them. The Sun-Jupiter system produces them, but for objects of everyday masses, at everyday separations and velocities, the waves are so faint as to be entirely undetectable in practice. For two black holes each, with masses of millions or billions of solar masses, orbiting each other at close range with high orbital velocities, the gravitational wave emission is much more significant. And it carries away energy. As the two black holes lose energy to gravitational waves, they spiral closer. As they spiral closer, the orbital velocity increases. the gravitational wave emission intensifies, and the process accelerates. Eventually, the two black holes merge, joining into a single, more massive black hole, and producing a final burst of gravitational wave emission in the process. The final merger of two supermassive black holes is one of the most energetic events that can happen in the universe. The gravitational wave burst, at the moment of merger, carries an enormous amount of energy in some cases. The mass equivalent of several solar masses is radiated away as pure space-time ripples in a fraction of a second. And then it is over. The two separate objects are gone. In their place is a single, more massive black hole, settling into its new configuration, slowly radiating away any residual distortion in its shape through lower-level gravitational wave emission, and eventually settling into the smooth, featureless geometry of a rotating black hole in equilibrium. And then the quiet returns. The merger was energetic, in the abstract sense that physicists use that word. But it is over quickly. The resulting black hole is massive and calm. It sits at the center of the merged galaxy, which is itself settling into a new equilibrium after the disruption of the merger. Stars that were scattered by the gravitational chaos of the merger event slowly find their new orbits. Gas that was stirred up settles or falls inward. And the central black hole, heavier for the merger, waits in its quiet gravitational presence, while everything around it slowly finds its new shape. The patience of this entire process, the millions or billions of years that each stage requires, the incremental accumulation of mass through slow accretion, the long spiraling approach of two black holes in a binary system, the eventual gentle completion of the merger and the quiet that follows, is the most defining feature of how supermassive black holes grow. They do not rush. They cannot rush. The processes involved have their own timescales, set by the physics of angular momentum and radiation pressure and gravitational wave emission, and those timescales are long. There is no shortcut. There is only the long, slow accumulation of time. When you think of the black hole at the center of the Milky Way, 4 million solar masses of patience and gravitation sitting at the center of a slowly turning galaxy, and you try to imagine the history that produced that mass, you are imagining billions of years of slow accumulation. The gas that spiraled in, grain by grain, in cosmic terms. The smaller galaxies that merged with the Milky Way in its past, their central objects contributing mass to the growing central black hole. The long epochs between active phases, when little material was falling inward and the mass grew only imperceptibly. All of that is contained in the 4 million solar masses that hold the Milky Way's rotation in place tonight. The mass is the record of the patience. No one has ever seen a supermassive black hole in the way you see a star. No bright point of light hanging in the sky. No steady glow that confirms its presence at a glance. No immediate visual certainty that says, there it is. A star announces itself without interpretation. It arrives as light that has traveled across space and still remains self-evident when it reaches the eye or telescope. A supermassive black hole does not offer that kind of clarity. It does not shine. It does not emit light in any conventional sense. In its deepest region, even the light produced by surrounding material cannot escape once it crosses the boundary known as the event horizon. What remains is not a visible object, but a region defined entirely by its influence on everything around it. This is why black holes are never observed directly. They are not objects that can be photographed in isolation like planets or stars. They are inferred through effects, through how they shape motion, bend light, heat gas, and organize the behavior of entire galactic centers. A black hole is defined by the way it changes the environment around it, not by any light it produces on its own. It is a presence known through consequences, not appearance. And because of this, the evidence for supermassive black holes always takes the form of convergence, many different observations, each incomplete on its own, but all pointing toward the same underlying structure when placed together. One of the clearest forms of evidence comes from motion itself. When astronomers observe the stars near the center of the Milky Way over long periods of time, they are not simply seeing points of light shifting in the sky. They are watching a gravitational system unfold with precision. These stars trace out elliptical orbits around an unseen central point, following the same mathematical rules that govern all gravitational motion. There is no randomness in their paths. Each orbit is predictable, repeatable, and consistent with the presence of a single dominant mass at the center of their motion. Some of these stars pass extremely close to that central point. As they approach, their speeds increase dramatically, reaching a small but measurable fraction of the speed of light before they swing around and move back outward along their elongated orbits. These high-speed passages are not chaotic. They are structured, periodic, and stable over decades of observation. From these orbital shapes and velocities, the mass of the central object can be calculated with remarkable precision. The result is consistent, approximately 4 million times the mass of the Sun, concentrated within a region so small that it cannot be explained by any known cluster of ordinary objects. That concentration matters. A mass of that size, packed into such a limited volume, cannot remain stable if it were composed of individual stars or stellar remnants. A dense cluster of that magnitude would collapse, interact, and radiate in ways that would make it visible in other wavelengths. It would not remain dark. The absence of such light is itself a clue. The only known structure capable of holding that much mass in such a confined region, while remaining invisible in emitted light, is a supermassive black hole. This same principle deriving invisible mass from orbital motion has been applied far beyond the Milky Way. In other galaxies where resolution allows astronomers to track either individual stars or the collective motion of gas clouds, the same pattern emerges. Objects orbit too quickly around a central point that emits no light. Gas rotates as though held by a deep gravitational well that cannot be explained by visible matter alone. Wherever the measurements are precise enough, the conclusion is consistent. A compact, massive, invisible object lies at the center. The method changes from galaxy to galaxy, but the inference remains the same. Light itself provides another layer of evidence, though in a different way. As light travels through space, its path is shaped by gravity. This bending is subtle under ordinary conditions, but becomes increasingly pronounced near extremely massive objects. Around a supermassive black hole, space-time is curved so strongly that light can follow closed or near-closed paths around the central region. Instead of moving in a straight line, outward or inward, photons can orbit briefly, trapped in unstable circular trajectories just outside the event horizon. This creates a distinctive observational pattern. When we observe the region around a supermassive black hole, we do not see a solid surface or a glowing core. Instead, we see a structure formed by light itself, an outer ring of brightness shaped by hot gas, surrounding a central dark region where light cannot escape. This dark region is not an object in the traditional sense. It is a shadow, created by the absence of light from within a boundary where escape is impossible. The bright ring is not a physical edge either. It is light that has been bent, redirected, and focused by the extreme curvature of space-time. The resulting image is not a photograph of a black hole in the everyday sense. It is a map of gravitational effects rendered in light. What we observe is not the black hole itself, but the imprint of its presence on everything around it. The geometry of that imprint matches theoretical predictions with striking precision, reinforcing the interpretation that what we are seeing is not illusion or artifact, but the direct consequence of extreme gravitational structure. Capturing such an image requires extraordinary observational capability. No single telescope can achieve the necessary resolution. Instead, astronomers use a technique that links radio observatories across the Earth into a single virtual instrument. By synchronizing measurements from widely separated locations, the effective size of the telescope becomes comparable to the diameter of the planet itself. This allows for resolution fine enough to distinguish the shadow-scale features of nearby supermassive black holes. The images produced by this method reveal exactly what theory predicts: a dark, central shadow surrounded by a luminous ring. The structure is not symbolic or approximate. It is quantitatively consistent with models derived from general relativity. The size of the shadow corresponds to the expected gravitational boundary. The brightness distribution in the ring matches predictions of how hot gas should behave near such an object. The alignment between theory and observation is not incidental, it is cumulative, emerging across multiple systems and multiple measurement techniques. This consistency is one of the most important aspects of black hole science. No single method is sufficient on its own. Each observation provides only a partial view. Stellar motion tells us about mass distribution, but not internal structure. Light bending reveals space-time curvature, but not feeding processes. Jets reveal energetic activity, but not precise mass. Gravitational lensing shows distortions, but depends on alignment and distance. Each method has limits. But when combined, they form a coherent and self-reinforcing picture. General relativity plays a central role in connecting these observations. The theory describes gravity not as a force in the traditional sense, but as the curvature of space-time itself. Massive objects distort the geometry around them, and this distortion determines how matter and light move. Near a supermassive black hole, this curvature becomes extreme enough to produce effects that are measurable across vast distances. The predictions of this framework, orbital dynamics, light bending, shadow size, energy emission patterns, are not vague or qualitative. They are precise and testable. What makes the observational agreement so significant is not just that the predictions work, but that they work across such different contexts. The motion of stars in the Milky Way, the structure of jets in distant galaxies, the lensing patterns of galaxy clusters, and the direct imaging of black hole shadows all arise from different physical regimes. Yet all of them align with the same underlying description of gravity. This convergence suggests not a set of isolated coincidences, but a consistent physical reality being observed through multiple independent channels. Jets offer another striking form of indirect evidence. In some galaxies, narrow beams of energetic plasma extend outward from the central region for distances that can span thousands or even millions of light-years. These jets are not random emissions. They are highly structured, aligned with the rotation axis of the central system, and powered by processes occurring in the immediate vicinity of a supermassive black hole. The energy required to sustain such jets cannot come from ordinary stellar processes. It must originate from the gravitational energy released by matter falling into a deeply curved spacetime. Even though the jets extend far beyond the visible boundaries of their host galaxies, their origin can be traced backward. Their alignment, composition, and energy profile all point toward a compact central engine. The further one follows the jet inward, the more constrained the possible explanations become. until only one remains consistent with all observations: a supermassive black hole at the center, converting gravitational energy into directed outflows of plasma. Gravitational lensing provides yet another window. When a massive galaxy lies between us and a more distant light source, its gravity bends the light traveling toward us. This can produce arcs, rings, or multiple images of the same distant object. The precise pattern of distortion depends on how mass is distributed within the foreground galaxy, including the contribution from its central black hole. By analyzing these distortions carefully, astronomers can infer the presence and mass of otherwise invisible central structures. Lensing is especially powerful because it does not rely on seeing the black hole's immediate surroundings. It depends only on how mass shapes space-time on large scales. Even in galaxies too distant for individual stars to be resolved, the imprint of the central mass can still be detected through its gravitational influence on background light. In this way, lensing extends black hole detection to regions of the universe where other methods cannot reach. Taken individually, each of these methods provides only partial insight. Stellar orbits reveal mass, but not structure. Light bending reveals geometry, but not composition. Jets reveal energy, but not precise location. Lensing reveals distribution, but not dynamics. But when considered together, they converge on a single conclusion. At the centers of galaxies, there exist objects that are extremely massive, extremely compact, and completely dark in emitted light. Their presence is not speculative. It is inferred through repeated, consistent, and independent lines of evidence. What emerges from this convergence is a kind of observational certainty that does not rely on direct visual confirmation. Instead, it relies on coherence. Every measurable effect, motion, light, energy, distortion, fits into a single framework. The black hole is not seen directly, but it is known with a kind of structural confidence that comes from the agreement of many independent measurements. In the end, supermassive black holes are invisible not because they are hidden, but because visibility is not part of their nature. They are not objects that emit light. They are structures that define how light behaves in their vicinity. And so, paradoxically, the universe allows us to know them precisely because they cannot be seen directly. The absence of light becomes its own form of signal, and from that signal, across vast distances and timescales, we build a picture of some of the most massive and quiet structures in existence. There is a relationship between a galaxy and its central black hole that goes beyond simple proximity, beyond the idea of one object sitting inside another, like a feature inside a container. It is a relationship written into the way both of them form, evolve, and settle across billions of years. The two are not separate in the way everyday intuition might suggest. They are not independent actors sharing space by coincidence. Instead, they behave more like parts of a single long-lived system, each shaping the conditions under which the other exists, each carrying subtle traces of the other's influence in their structure. A galaxy without a central black hole would not simply be the same system missing a component. It would be fundamentally different in how its central regions evolve, how gas behaves, how stars form, and how the innermost structure organizes itself over time. Likewise, a supermassive black hole without a galaxy would not be the same kind of object in any meaningful astrophysical sense. It would lack the vast reservoir of gas, dust, and stellar material that allows it to grow into the immense structures observed in the centers of galaxies. The pairing is not accidental. It is deeply embedded in the history of how cosmic structure builds itself. This relationship is shaped over long timescales through a process often described as feedback, though the word feedback can sound too mechanical for something so vast and gradual. It is less like a loop in a machine and more like a slow conversation between gravity, radiation, and matter. When a supermassive black hole begins to actively feed, drawing in gas from its surroundings, that gas does not simply disappear quietly. As it spirals inward, it forms a hot, dense accretion structure that releases enormous amounts of energy. This energy does not remain confined near the black hole. It spreads outward into the surrounding environment. The effect of this outward energy is subtle but powerful. Gas in a galaxy exists in a delicate balance between gravitational collapse and thermal support. When it is cool and dense enough, it can clump together, forming new stars in quiet regions of space. But when that gas is heated, even slightly, its behavior changes. It becomes more diffuse, more resistant to collapse, and more likely to remain spread out rather than condensing into new stellar systems. In this way, the energy released by a feeding black hole gently suppresses the conditions needed for new star formation in its immediate surroundings. At the same time, this same heating process reduces the amount of gas available for the black hole itself to continue feeding. As gas is heated and pushed outward, its density drops. It becomes more difficult for gravity to draw it inward efficiently. The black hole, in a sense, modifies its own supply conditions through the very act of consuming material. What begins as a phase of active growth naturally transitions into a phase of reduced activity, not because anything external forces it to stop, but because the environment it shapes becomes less favorable for continued rapid feeding. Over long periods of cosmic time, this interplay leads to a kind of large-scale balance between the mass of the central black hole and the mass of the surrounding stellar bulge of the galaxy. The system self-organizes into a state where neither component grows without limit relative to the other. The black hole grows until its energetic output is sufficient to regulate the inflow of gas in the central regions. The galaxy continues to form stars wherever gas remains available, but the most intense growth phases gradually give way to more stable and regulated behavior. The result of this long interaction is not a static system, but a settled one. A galaxy and its central black hole reach a kind of equilibrium state, where both continue to exist, both continue to evolve slowly, but neither dominates in a runaway way. The most intense periods of change are behind them. What remains is long-term stability, punctuated by occasional activity rather than constant transformation. Most supermassive black holes in the universe are observed in exactly this kind of quiet state. They are not continuously consuming large amounts of matter. They are not surrounded by bright, luminous accretion disks at all times. Instead, they spend most of their existence in low-activity phases, where only small amounts of gas drift inward occasionally. In these states, the central regions of galaxies appear relatively calm. The black hole is still there, still massive, still exerting its gravitational influence, but it is not currently undergoing dramatic feeding events. The more active phases, where black holes consume matter at high rates and produce enormous amounts of radiation, do occur, but they are comparatively rare in the lifetime of a galaxy. These phases are often tied to specific conditions, such as the availability of large gas reservoirs or the disturbances caused by galactic interactions. When they do occur, they can dramatically reshape the central regions of galaxies, but they are not the default state. The default state is quietness. The Milky Way provides a clear example of this quiet condition. Its central black hole, known as Sagittarius A, is not currently in an active feeding phase. The amount of material reaching the immediate vicinity of the event horizon is low. There is no large, sustained accretion disk producing intense radiation. Instead, the center of the galaxy is relatively subdued. Occasional small flares occur when localized clumps of gas move through the inner regions, but these events are brief and limited in scale. They do not represent sustained activity. They are more like small ripples in an otherwise calm system. This quiet state is not unusual. It is, in fact, the most common state for galaxies like the Milky Way. Over cosmic time, galaxies spend far more of their existence in these settled conditions than in active phases. The intense periods of black hole feeding and luminous activity are temporary episodes embedded within much longer stretches of stability. In this sense, the Milky Way is not in a special or unusual condition. It is in its mature phase, where growth has slowed and the system is evolving gradually rather than explosively. Even in this quiet state, the galaxy is not static. It continues to rotate, with its spiral arms slowly sweeping through space over hundreds of millions of years. Stars continue to orbit the central region, each following its own gravitational path shaped by the combined mass of the galaxy. The central black hole remains at the gravitational center, not as an active participant in daily galactic change, but as a stabilizing presence that defines the structure of the inner system. Everything orbits around it, even if it is not actively interacting with everything. But the Milky Way is not isolated in its future. Another galaxy, Andromeda, is approaching. It is the nearest large galaxy to our own, visible as a faint, diffuse glow in the night sky. For billions of years, the two galaxies have been moving toward each other under the influence of their mutual gravitational attraction. This movement is slow on human timescales, but inevitable on cosmic ones. Eventually, the two systems will meet. This meeting will not resemble a collision in the everyday sense. Space within galaxies is mostly empty, and so the stars themselves will rarely collide directly. Instead, the encounter will unfold as a long gravitational interaction, where the shapes of both galaxies become distorted. Spiral arms will stretch and warp. Stellar orbits will be reshaped. Over time, the two galaxies will pass through each other, separate again, and then gradually fall back together. This process will repeat over multiple passes, each time redistributing stars and gas more thoroughly, until the two systems finally merge into a single, larger galaxy. At the centers of these galaxies lie their respective supermassive black holes. The black hole at the center of Andromeda is more massive than Sagittarius A, reflecting differences in the histories of the two galaxies. As the merger progresses, these two central black holes will eventually sink toward the center of the newly forming combined galaxy. This movement is not instantaneous. It occurs over millions to billions of years, driven by interactions with surrounding stars and gas that slowly remove energy from their orbits. As they draw closer, the two black holes will eventually form a bound pair, orbiting one another in a slow, tightening spiral. This binary system will gradually lose energy through gravitational interactions with the surrounding environment. In the final stages of their approach, the emission of gravitational waves becomes the dominant mechanism driving them together. These waves carry energy away from the system, allowing the two black holes to spiral inward until they finally merge. The result of this long process will be a single, more massive, supermassive black hole at the center of the merged galaxy. This future galaxy is sometimes referred to informally as Milky Way, a name that reflects the blending of its two progenitors. But the name itself is less important than the process it represents, a slow, natural continuation of galactic evolution that unfolds over timescales far beyond human experience. Even this dramatic event, when viewed on cosmic scales, is not sudden. The entire sequence of interaction, from initial approach to final merger, spans billions of years. It is not an explosion, or a moment of change. It is an era of gradual transformation, in which structure is reshaped through continuous, subtle gravitational influence rather than abrupt disruption. At the same time, the universe as a whole is expanding. Space itself is stretching, causing distant galaxies and galaxy groups to move away from one another. On very large scales, this expansion dominates over gravitational attraction, gradually increasing the separation between structures that are not already bound together. Over extremely long timescales, many galaxy groups will become isolated from one another, each becoming a self-contained island of matter surrounded by ever-increasing emptiness. Within each of these isolated regions, galaxies will continue their internal evolution. Stars will age and fade. New star formation will slow as gas reserves are gradually depleted. The galaxies will become quieter, their luminous activity diminishing over time. And at the center of each one, the supermassive black hole will remain, continuing to exist long after the surrounding stars have gone dark. In this way, the central black holes outlast the luminous life of their galaxies. They persist through phases of activity and quiet, through periods of intense feeding and long intervals of stillness, and eventually through the transition into a universe where stars are no longer forming in significant numbers. They remain as the most enduring gravitational structures within their systems, anchoring the centers long after the visible structure has faded. Across all these scales, a rhythm becomes visible. Activity followed by quiet. Growth followed by stability. Formation followed by maturity. The universe does not move through abrupt transitions, so much as it moves through long, layered cycles of change, each embedded within the next. And at the center of these cycles, at every scale where gravity gathers matter into organized structure, the supermassive black hole remains as the most stable point, not because it resists change, but because its timescales of change are so vast that, from almost any perspective, it appears still. Beyond the mergers, beyond the quieting of star formation, beyond the slow reddening of aging galaxies and the gradual dimming of the universe's total light, there is a far future that stretches outward into time, in a way that stops feeling like a timeline and starts feeling more like a vast, continuous depth. The universe is approximately 13.5 billion years old, a number that already places human experience into an almost unimaginable scale. Yet even that immense history is brief compared to what still lies ahead. The processes that continue forward are projected across spans of time so long that ordinary language begins to lose precision, where even words like long or enduring feel too small to carry the meaning they are asked to hold. In this distant future, measured in trillions of years and far beyond, the universe continues its slow unfolding. Matter does not suddenly change its nature. Gravity does not stop operating. Instead, everything that exists simply moves further along the tendencies already present today. Structures become more isolated. Energy becomes more spread out. Light becomes more rare. And through all of this gradual thinning, supermassive black holes remain as some of the most stable and persistent features in the entire cosmic landscape. Stars, by contrast, have lifetimes that are finite in a way that feels almost gentle when compared to these cosmic horizons. The most massive stars live fast lives, burning through their fuel in only millions of years, luminous and intense, but brief in the language of cosmic time. Stars like the Sun occupy a quieter middle ground, sustaining themselves for around 10 billion years before gradually shifting away from stable fusion and entering their later stages of evolution. Even the smallest and most efficient stars, the red dwarfs, which burn their fuel with extraordinary patience, are not truly permanent. They stretch their lifetimes into trillions of years, far longer than the current age of the universe. But even they are still part of a cycle that eventually concludes. Over these vast spans of time, every star will eventually exhaust its fuel. Hydrogen in their cores will run out, fusion will cease, and they will transition into later stages of stellar evolution. Some will shed their outer layers gently, leaving behind cooling stellar remnants known as white dwarfs. Others will collapse more dramatically, forming neutron stars or stellar mass black holes. The universe will not suddenly lose its stars in a single moment. Instead, it will gradually shift into an era where new stars are no longer forming in significant numbers, and existing stars are steadily aging out of their luminous phases. One by one, the familiar points of light that define galaxies today will fade. There will come a time, far beyond anything connected to human history, or even the existence of Earth, when the last star in every galaxy has gone dark. At that point, the universe will enter what is sometimes described as the stellar remnant era, though it is less an era in the usual sense, and more a slow transition into deep darkness. Galaxies will still exist in structure, but they will no longer be filled with shining stars. Instead, they will be populated by the remnants of former stellar lives, cooling white dwarfs, dense neutron stars, and black holes formed from earlier generations of stellar collapse. The light that once filled galaxies will be largely gone, replaced by faint infrared glows and the gravitational presence of mass that no longer shines. In this quiet and darkened universe, supermassive black holes at the centers of galaxies remain. Unlike stars, they do not rely on fusion. They do not produce energy through burning fuel. Their existence is not tied to a finite supply of internal energy that must eventually run out. Instead, they are governed primarily by gravity and geometry, by the curvature of space-time itself. When isolated, with no significant matter falling into them, they do not grow or change in dramatic ways. Their evolution becomes extraordinarily slow, governed by processes so subtle that they only become meaningful over timescales that dwarf everything else in the universe. One such process involves the gradual emission of extremely faint radiation from just outside the event horizon. This phenomenon arises from the interplay between quantum effects and the curved structure of spacetime near the black hole's boundary. Over immense spans of time, this radiation carries away tiny amounts of energy, causing the black hole to lose mass very slowly. This process is often described as black hole evaporation, but the word evaporation can be misleading if it suggests something familiar or fast. Nothing about it resembles evaporation in the everyday sense. It is not visible, not measurable on short timescales, and not something that changes the appearance of a black hole in any humanly meaningful interval. The timescales involved are so extreme that they challenge comprehension. For a black hole comparable to the mass of a star, the evaporation time already exceeds the current age of the universe by enormous factors. For a supermassive black hole, the effect is magnified dramatically. When a black hole contains millions or billions of solar masses, the timescale for complete evaporation becomes so long that it extends into numbers that are difficult to interpret as physical quantities at all. In many estimates, the evaporation time is expressed as a power of 10 so large that writing it in full would require more digits than there are particles in the observable universe. In practical terms, this means that supermassive black holes are effectively permanent on any timescale that has ever mattered to cosmic history. They will persist long after the last stars have faded. They will remain long after galaxies have stopped forming new structures. They will continue through eras in which the universe becomes increasingly dark, increasingly diffuse, and increasingly dominated by isolated remnants rather than active processes. If there is a single category of object that defines endurance in the universe, it is these silent gravitational centers. As time continues forward, the large-scale structure of the universe itself evolves in ways that further isolate these black holes. The expansion of space causes distant galaxies and galaxy clusters to move away from one another. Over extremely long timescales, regions that are currently part of the same observable structure may drift beyond each other's ability to interact. Light emitted from one region will no longer be able to reach another. Each gravitationally bound system becomes increasingly self-contained, an isolated island of matter surrounded by an expanding void. Within these isolated systems, galaxies may still interact for a time. They may merge with one another, their stars gradually rearranging under the influence of combined gravitational fields. When galaxies merge, their central black holes eventually move toward one another, drawn inward over long periods through interactions with surrounding matter. These black holes can form binary systems, orbiting each other in slow, tightening spirals. Over time, they merge into a single, larger black hole, releasing energy in the form of gravitational waves that ripple through space-time itself. But even these events are rare on the largest timescales, and they become less frequent as the universe continues to expand and matter becomes more diffuse. Eventually, even within galaxy clusters, the process of interaction slows to a near standstill. Stars that have not already been consumed or ejected gradually find themselves in long, stable orbits or drifting paths that take them far from central regions. Some are captured by black holes. Others are flung outward entirely, leaving the gravitational influence of their original systems. What remains is a sparse environment dominated by remnants rather than active structures. In one of the most extreme projections of cosmic evolution, a galaxy cluster may eventually collapse much of its remaining bound mass into a single, enormous supermassive black hole. This object would represent the final concentration of gravitational assembly within that region of space, a culmination of billions of years of mergers and inward drift. Even then, the black hole does not represent an endpoint in the usual sense. It does not mark completion or finality. Instead, it simply continues to exist, now even more isolated than before, surrounded by an increasingly empty universe. From there, even this largest consolidated black hole would begin its own extremely slow evaporation process. Over unimaginable timescales, it would gradually lose mass through the same faint quantum effects that govern all black hole evaporation. The radiation it emits would be extraordinarily weak, spread across vast regions of space, and diluted to the point where it would be almost impossible to distinguish from the background energy of the universe itself. And yet, in principle, it would still occur. The transformation of mass into radiation would continue, steadily and without interruption, over periods of time so long that they cease to have meaningful comparison to anything in human experience. Through all of this, there is no urgency. Nothing in this description is happening in a way that connects to immediate futures or personal timelines. The far future of the universe is not something that arrives suddenly or demands attention. It is an extension of the present laws of physics, carried forward into durations so long that they become abstract rather than experiential. It is less a prediction than a conceptual horizon, a way of understanding how persistent the underlying structure of reality truly is. Supermassive black holes, in this context, stand out not because they are active or dramatic, but because they are enduring. They are among the last structures that remain meaningful when everything else has changed. They do not rely on the presence of stars. They do not depend on ongoing formation processes. They exist through stability rather than activity, through gravity rather than energy production. In a universe that becomes increasingly quiet over time, they represent a form of persistence that is almost architectural in nature, as though they are the deep support beams of cosmic structure itself. From the perspective of a single human lifetime, or even the entire history of civilization, none of this is immediate. It is not something that will be observed, experienced, or directly encountered. It exists in the same way that deep geological time exists on Earth, real, continuous, and unfolding, but far beyond the scale of daily awareness. And yet, even in its remoteness, it offers a kind of perspective. It reveals that the universe is not defined by sudden endings or sharp transitions, but by gradual changes that unfold across unimaginable spans of time. So when all of this is held together, the fading of stars, the isolation of galaxies, the persistence of supermassive black holes, and the extremely slow evolution of space-time itself, the overall picture is not one of collapse or disappearance. It is one of continuation. The universe does not stop. It does not reach a final moment. It simply moves forward, step by step, over scales of time that stretch beyond ordinary comprehension. And at the centers of galaxies, even as everything around them changes, the supermassive black holes remain. Quiet, stable, patient in a way that is not emotional, but structural, holding their position in space, shaping motion around them, and continuing their long existence in a universe that is always changing, but never suddenly ending. The Milky Way is still turning. Right now, even as your awareness begins to soften and the edges of thought start to blur into something quieter and more fluid, the galaxy continues its long, unhurried rotation. It does not change pace for anything on its surface. It does not speed up or slow down in response to observation. It simply continues, as it has for hundreds of millions of years, in a motion so gradual that no single human lifetime could ever perceive even a fraction of it directly. One full rotation of the Milky Way takes on the order of hundreds of millions of years, a span so vast that it dissolves ordinary intuition about time altogether. Within that rotation, every star is following a path shaped by gravity. Each one is tracing an orbit that is not random, not chaotic, but quietly structured. The stars in the spiral arms are not fixed to their positions like static points on a diagram. Instead, they are flowing along gentle arcs, slightly faster or slower depending on where they sit in the galaxy's gravitational field, weaving a pattern that looks still only because it is so large and so slow. The spiral arms themselves are not rigid structures either. They are more like waves of density moving through the galactic disk, regions where stars momentarily gather before continuing on their long journeys around the center. The solar system is one of those traveling points of light, embedded within one of the Milky Way's spiral arms. It moves along with its surrounding stars, not separated from them in any meaningful way at this scale. Everything here is in motion together. The sun, the planets, the asteroid belts, even the distant icy objects far beyond Neptune's orbit are all participating in this same slow galactic orbit. From a cosmic perspective, nothing in your immediate experience is stationary. The ground beneath you, the air around you, the planet as a whole, all of it is carried along in this shared path around the center of the galaxy. And at the center of all this turning, there is Sagittarius A star. It does not announce itself. It does not emit light in the way stars do. It does not draw attention through brightness or color. Instead, it exists as a region of extreme gravitational influence, containing roughly 4 million times the mass of the Sun, compressed into a space that is, by comparison, astonishingly small on galactic scales. It is not a surface you could ever approach in any ordinary sense. It is not an object with edges and texture. It is a condition of space itself, a point around which the entire inner structure of the Milky Way is organized. The stars closest to it move in tight, fast orbits, circling an invisible center in patterns that reveal its presence without ever showing it directly. These orbits are not abstract theoretical predictions. They are observed, tracked, and measured over long periods of time, forming a kind of celestial choreography that only makes sense if something extremely massive is holding everything in place. The motion of these stars is one of the clearest indications that Sagittarius A star is not a collection of ordinary objects, but a single supermassive black hole. Despite its mass, it is not an active beacon of energy. It is quiet. It is not currently consuming large amounts of surrounding matter. Instead, it sits in a relatively calm state, occasionally interacting with small amounts of gas or dust that drift too close, producing brief and subtle flares of energy before returning to stillness. Even these flares are not dramatic in cosmic terms. They are variations within a much larger pattern of quiet persistence. Around this central presence, the entire galaxy continues its rotation. The disk of stars, gas, and dust is shaped by the gravitational field that stretches outward from the center, but the influence is not forceful in a directional sense. It is more like a deep curvature in the structure of space, guiding motion rather than pushing it. Everything that orbits is responding to that curvature, tracing paths that are stable over immense periods of time. Across the observable universe, this pattern repeats itself again and again. Billions of galaxies exist, each one with its own structure, its own arrangement of stars and gas, and almost all of them with a central region of extreme mass. These central regions vary in size and activity. Some are relatively quiet, like our own. Others are far more active, surrounded by glowing disks of infalling material that radiate enormous amounts of energy. But beneath these differences in appearance, the underlying structure is the same. Each galaxy rotates around a central gravitational anchor. These anchors are supermassive black holes. They do not function like engines or sources of energy. They do not generate motion in the way a motor would. Instead, they define the geometry of motion itself. Their presence shapes the orbits of stars and gas clouds at vast distances, ensuring that the entire galactic system remains organized over time. Without them, the structure of galaxies would be fundamentally different, less stable, less coherent, more diffuse. With them, galaxies acquire a center of balance around which everything else can move. Even in galaxies far beyond our own, separated by millions or billions of light years, the same principle applies. A central mass holds the system together. Stars orbit. Gas flows. Spiral arms form and dissolve over time, but the overall pattern of rotation persists. The universe, on large scales, is not random. It is structured, and that structure is deeply tied to the presence of these invisible centers. There is something quietly uniform about this repetition. It is not repetition in a mechanical sense, but in a structural sense. Like a pattern that emerges naturally whenever matter gathers in sufficient quantity over long periods of time. Wherever enough gas and dust accumulate, gravity begins to draw them inward. Stars form. Clusters form. Galaxies form. And at the center of these systems, matter tends to concentrate further, eventually forming a supermassive black hole. Not because it is planned, but because it is the natural outcome of long, slow accumulation under gravity. In this way, the universe becomes filled with centers. Not visible ones, but gravitational ones. Not points of light, but points of structure. Each galaxy becomes a kind of slow, rotating system held together by something that cannot be seen directly, but can always be inferred through motion. And you are part of this turning. The atoms that make up your body were formed in stars long before the solar system existed. Those stars were part of earlier generations of galactic evolution, cycles of formation and dispersal that unfolded over billions of years. The material that composes you has been through many stages of cosmic history, carried through different stars, different regions of space, different configurations of matter, before eventually becoming part of a planet orbiting an ordinary star in a quiet region of the Milky Way. That planet is not stationary. It is moving. It is orbiting the Sun, and the Sun itself is orbiting Sagittarius A star. In a very real physical sense, your body is participating in that same motion. You are not outside the galaxy, observing it from a detached perspective. You are inside it, fully embedded in its structure, carried along in its slow rotation, whether you are aware of it or not. The idea of center, in this context, is not something distant or separate from you. It is a structural feature of the system you belong to. Sagittarius A star is not the center of something you are merely looking at from afar. It is the center of the environment that contains you. It defines the large-scale motion of everything around you, including the star that gives you light and warmth. In that sense, your existence is already shaped by its presence in every moment, even if that presence is not something you ever directly perceive. This is not something that requires attention or reaction. It does not ask anything of you. It simply describes the way motion is organized on a galactic scale. Everything follows its path. Everything continues along its orbit. Nothing is being interrupted. And so, as awareness continues to soften, there is a sense in which this entire structure, the rotating galaxy, the quiet center, the orbiting stars, the distant repetition across billions of systems, can be held in the mind as a single continuous motion. Not as separate pieces, but as one vast, slow turning. The universe is turning. The centers are holding. The light from ancient quasars continues its long journey through space, carrying echoes of activity that ended long before Earth formed. In distant galaxies, supermassive black holes sit in states of deep quiet, their mass shaping entire systems without visible effort. Even in their most active phases, they are governed by balance, by inflow and outflow, by structure and constraint. Most of the time, they are not active at all. Most of the time, they are simply there. And in that stillness, across unimaginable distances, the same pattern continues. Motion organized around centers. Structure held by gravity. Time unfolding without urgency. Nothing is rushing. Nothing is collapsing in a way that demands attention. Everything is simply continuing in its own scale of time. So as this moment softens further, there is nothing left to solve or follow or hold on to. Only the awareness that you are part of something already in motion, something vast and stable and ongoing, something that does not require interruption to continue existing. The Milky Way is still turning, and it will continue turning long after this moment has passed. Sleep well, and good night.